Hi guys, my name is Peng Hongyi, and it's a great honor to be here to present our work, ODDITY. ODDITY is an anomaly detection framework that leverages contrastive representation learning and also ensemble learning. Let's start with the background. Nowadays, network administrators must deal with continually evolving threat landscapes, increasing attack intensity and complexity. So, timely anomaly detection becomes increasingly important in network security, as it is often the front line of defense and threat hunting. In fact, anomaly detection has become one of the main research priority for both academia and industry. Simply speaking, anomaly detection is all about finding abnormal patterns in normal activities, and it's pretty straightforward to consider the anomaly detection problem as a binary classification task in machine learning. We all know that there are supervised and unsupervised learning in machine learning. However, to use them for anomaly detection is not trivial. Supervised methods have decent performance when there is good feature engineering and a large amount of data, but anomaly detection, especially network anomaly detection, often suggests very expensive annotation for malicious activities. Also, when dealing with an extremely imbalanced dataset, like the case in network anomaly detection, the performance of the supervised method will not be that satisfying. And luckily, we got unsupervised methods that are good at extracting features and do not require labels. Recently, it has become more and more common for anomaly detection techniques to combine supervised method with unsupervised feature extractors, and this is called semi-supervised method. Another trait of anomaly detection that's worth noticing is that even if we use some sort of unsupervised feature extractor, one is often not enough. For example, a representation that can be utilized to detect a sudden surge in network traffic may be not that effective in detecting network anomalies caused by something like malware, intrusion, or misuse. So this issue has compelled researchers to adopt ensemble learning to effectively combine many unsupervised feature extractor. As I just said, to address the aforementioned issues, the current state of art anomaly detection techniques often adopt a semi-supervised ensemble approach. Basically, they create an ensemble of multiple unsupervised learners, which we also call it base learners. Base learners aim to extract more abstract features, and these features are fed into a supervised classifier, which is often referred to as a meta-learn. Then, meta-learning is trained with labels and to give final predictions. As the major component of semi-supervised ensemble learning, the quality of ensemble is critical to the overall performance. Previous study has proved that the success of ensemble learning requires a good trade-off between diversity and accuracy. And actually, it's intuitive to believe that statement. On the one hand, combining a bunch of good but exactly identical base learners apparently will not result in any improvements. On the other hand, if we combine different but bad base learners, it should exacerbate the added error. Previously, work balanced the trade-off between diversity and accuracy using two approaches. First of all, maybe they can select different types of base learners. This is because one type of base learner often suggests one base learning algorithm, and it is reasonable to believe that they are some sort of diverse. Or a more recent method, add an extra feature selection procedure, which means among all those features extracted by base learners, we can select the most diverse subset given some metrics of similarity or distance. The problem with existing work is that if we want to adopt the base learner selection approach, we need to specify what base learner to use manually. And this actually limits generalization because when it comes to deployment, it often requires reselecting base learner using cross-validation or previous results. Additionally, since the diversity of base learners relies on our selection and also the internal process, which means the diversity is not guaranteed throughout the training. Furthermore, if we take the feature selection approach, which means we promote the diversity through feature selection, the problem with this approach is that it often requires expensive investigation on representation generated by each base learner and impairs the efficiency of the whole framework and makes the framework not end-to-end. So all those gaps has led us to fundamental questions: how to ensure a good trade-off between accuracy and diversity without bringing any extra selection steps. To address aforementioned questions, we propose a new end-to-end framework called ODDITY. In ODDITY, we introduce a set of homogeneous base learners called Diverse Autoencoders. Diverse Autoencoders learn to extract diverse and complementary features and then improve the performance of the whole framework. ODDITY does not require any selection, making it a pure end-to-end framework. And in terms of performance, we evaluate ODDITY on multiple datasets and show that ODDITY outperforms baselines in terms of both accuracy and efficiency. Last but not least, we investigate how black box evasion attacks impair the performance of supervised and semi-supervised anomaly detection techniques by deceiving the detector. We observe that due to the semi-supervised nature and disagreement among base learners, ODDITY is more resilient than other techniques against evasion attacks. So in the next slide, we will introduce the details of the diverse autoencoder. Training a diverse autoencoder involves three loss functions, namely reconstruction loss, contrastive loss, and diversity loss. The latter two aims to promote diversity, and in this slide, we're going to introduce the contrastive loss. So first of all, we will cluster the dataset into a few clusters, and this pre-clustering strategy avoids providing the same training data to each diverse autoencoder. Inspired by recent contrastive learning, we deemed a good representation should map data points within the cluster closely together, whereas data points from another cluster should be projected further apart. In this way, minimizing the contrastive loss function for all diverse autoencoder teach each encoder to extract the compact representation from the corresponding cluster. In other words, each diverse autoencoder becomes an expert on a subset of data. In this slide, we will introduce the diversity loss. For each diverse autoencoder, of course, we have the regular reconstruction loss just like any other autoencoder. But we also introduce a prediction level diversity loss. Here, prediction level means normally when we want to use an autoencoder for anomaly detection, we measure the reconstruction error. Higher reconstruction error means more abnormal patterns. So besides the contrastive learning laws introduced in previous slide, we also want each autoencoder to disagree with each other on whether a data point should be classified as anomalies or not. One way to design the diversity loss is we can average the pairwise similarity of all pairs of diverse autoencoders. However, computing the pairwise similarity is very computation intensive and significantly slow down the process. Thus, instead of computing pairwise similarity, we measure the dissimilarity between diverse autoencoders reconstructions and the average reconstruction. Although there is no widely accepted definition of diversity at this moment, we decide to choose 4 typical and common measurements of dissimilarity: variance, KL divergence, cosine similarity, and entropy, to investigate whether our design of diverse autoencoders helps in achieving a better trade-off between diversity and accuracy. We compare diverse autoencoder with normal autoencoders and some other baselines like randomNet and BAE. We train all of them on a toy dataset with exactly the same architectures, and in this figure demonstrates how the reconstruction and diversity loss vary with the number of epochs. For normal autoencoder, with the decrease of the reconstruction loss, the diversity loss drops to near 0, implying that features extracted by 2 ordinary autoencoders are almost the same. As a comparison, diverse autoencoders, like the red line here, provide significantly more diversity while achieving very low accuracy loss. When compared to randomization-based systems such as randomNet and BAE, diverse autoencoders deliver a higher level of accuracy while preserving a considerably higher level of diversity. To demonstrate the effect of improved trade-off achieved by diverse autoencoders to the final ensemble results, we train 2 diverse autoencoders on a small subset of a real network intrusion dataset. And we actually evaluate each diverse autoencoder's detection accuracy against various types of malicious attacks. Then we average the prediction score of each diverse autoencoders to generate the simplest ensemble of these diverse autoencoders. We again evaluate the ensemble's detection accuracy. The findings are summarized in table on the right. As you can see here, due to the training scheme of diverse autoencoders that promotes diversity, each diverse autoencoder is only capable of detecting a subset of attacks. For example, the types of attacks that diverse autoencoder 1 can detect and the attacks that diverse autoencoder 2 can detect are complementary. So as a consequence, combining diverse autoencoder 1 and diverse autoencoder 2 with even the simplest averaging results in perfect accuracy. Then we create a synthesized dataset to visualize why diverse autoencoder enhance anomaly detection. We color the decision region of each autoencoder into orange and blue so that all points within the decision region are predicted to be anomalies. As can be seen here, the decision areas of 2 regular autoencoders are largely overlapping, implying that without any method to promote diversity, the 2 regular autoencoder provides almost the same predictions. And combining them of course results in very marginal improvements. However, in the figure below, we can see like the two diverse autoencoders provide complementary prediction, and combining them, of course, can boost the overall performance. As mentioned before, semi-supervised ensemble learning require not only an ensemble of base learner, but also require a supervised meta-learner. The final meta-learner is also very important. So to find the best meta-learner for our diverse autoencoder, we first train various supervised classifier on the raw data, which is without DA here. Then we use diverse autoencoder to extract the feature and feed this generated feature to those supervised classifier. Then we measure the performance in AUPRC to assess like the efficiency of each supervised classifier in utilizing the diverse representation generated by diverse autoencoders. Although all supervised meta classifier benefit from the diverse representation extracted by DAs, as you can see here, gradient boosting ensemble method in ODDITY improves the most and achieves the best performance. Now we have the overall framework of ODDITY. ODDITY is a stacking-based three-stage framework that uses gradient boosting ensembles, GBE, introduced in last slide, to leverage both the raw data and the diverse representation generated by diverse autoencoders. In the first stage, we train diverse autoencoders in an unsupervised manner. In the second stage, use diverse autoencoder to extract features, which is like the hidden states of autoencoder, and then we augment the original data set with the extracted features. Finally, we feed this augmented data set to gradient boost ensemble, which is like the final meta supervised classifier. To evaluate the performance and applicability of ODDITY, we use several multidimensional data sets, and we also add 3 real network traffic data, namely KDD99, UNSWMB15, and IDS 2018. We randomly split every dataset so that 60% of the dataset is used for training and the remaining 40% is for testing. ODDITY is implemented using PyTorch and light gradient boosting machine. And due to the imbalanced nature of anomaly detection datasets, we use AUPRC as the metrics of our performance. Here is the results. We first evaluate the AUPRC score of our approach and other baselines on benchmarking datasets. So as you can see here, ODDITY has significant advantages over traditional supervised classifiers. And although gradient boosting ensemble, XGBold, and gradient boosting autoencoders can achieve satisfying results on most of the datasets, ODDITY still demonstrates uniformly superior performance. ODDITY variance, which is like we use the variance as a diversity loss, has the best AUPRC score in 5 out of 6 datasets and is 6% better than the state-of-art XGBold. Also, the comparison between ODDITY with gradient boosting autoencoder serves as like ablation studies for diverse autoencoder. The advantage of ODDITY over gradient boosting autoencoder illustrate that the accuracy and diversity trade-off achieved by diverse autoencoders can further improve the overall performance. Also, a better trade-off between accuracy and diversity achieved by ODDITY also leads to better ensemble results compared with randomization-based techniques such as RandomNet and BAE. Here we compare the performance of ODDITY and XGBold on real network datasets. As you can see here, ODDITY has higher AUPRC for KDD and UNSWMB15 datasets, which also resulting in an increased precision, recall, and F1 score. Moreover, ODDITY has lower false particle rates, which is a critical criterion for an anomaly detection system. ODDITY also has significantly advantage in terms of speed and runtime efficiency compared to XGBoost, as XGBoost requires feature selection to promote diversity. Here we investigate whether this feature generated by diverse autoencoders actually helps in final prediction. So we compare the feature importance map between ODDITY and pure gradient boosting ensemble. And we can see here that the added features extracted by diverse autoencoder play fairly a vital role in classification, and that's why we can achieve better performance with ODDITY. In the slide, we discuss the robustness of ODDITY against evasion attacks. Recent research has demonstrated that machine learning models output can be arbitrarily adjusted with a very small change into the input, and that means like anomaly detection systems are facing unprecedented threats. Like malicious people can fool and deceive the detectors by only introducing a very small minor perturbation to the original record. So it is often desired for anomaly detection system to be resilient against evasion attacks. Here we consider SIMBA attacks, which stands for simple black box attacks, which is a simple yet very powerful strategy that constructs data points to fool the detector based on previous query results. We launch attacks to the supervised method and also the semi-supervised method used before, and we choose datasets for this experiment that most anomaly detection approach achieve decent results, so that it will be more challenging for evasion attacks to bypass and to deceive the detector. And this figure illustrates how the success rate increase as the number of the query budget increase. Both supervised anomaly detection techniques like logistic regression, SVM, KNN-MLP, and also state-of-the-art ensemble method, XGBoost, and LGBM are very vulnerable to SIMBA attacks. Like within 30 queries, attacks can successfully deceive the detector. However, ODDITY is significantly more resilient than others. Even when the budgets of queries increase, ODDITY maintains low success rate. The reason behind ODDITY's resiliencies are the diverse autoencoder in ODDITY some sort of augments the input features which act as redundancy and error checking. Then additionally, the attacker is also unaware of the inner mechanism of diverse autoencoders, which implies that the attacker is dealing with two black boxes. Also, it's more difficult to deceive all diverse autoencoders simultaneously because we encourage disagreement among diverse autoencoders. So developing an attack mechanism that tricks all diverse autoencoders will become increasingly difficult. So in conclusion, ODDITY outperforms other supervised and semi-supervised techniques in terms of accuracy, efficiency, and also the resilience to evasion attacks. And ODDITY reduce model-centric bias by effectively combining representation learned by multiple diverse autoencoders. And the mechanism in diverse autoencoders that promotes diversity also relates to the fact that anomaly occurs for a variety of reasons in real neural traffic. It's more difficult for evasion attacks to deceive all diverse autoencoders simultaneously. And okay, that's all for my presentation.